So in all the tests, you were either able to calculate an intrinsic rate constant or it was given at a specific temperature. And you were eventually in all the tests required to calculate the true activation energy of this reaction. So just some frequently made mistakes that I encountered while marking the test. The first one is the illegal proration for the intrinsic rate constant with temperature. So yes, we use the ratio of the two rate constants at the two temperature, and the K0 dash, the intrinsic K0 dash value indeed cancels out. However, it is not true that this e to the minus e, that one will cancel out. Please just revise the appropriate maths, but this is typically an error made in desperation. Never ever make that mistake again. The second error is assuming that you are in the regime where falsified or apparent kinetics apply, therefore eta equal to 3 over the Thiele modulus, without testing or confirming that your Thiele modulus is indeed higher than 20 for both the scenarios that you were given. So in all the tests, you were given initial temperature and particle diameter moving to a different temperature and particle diameter. If you wanted to use this for the apparent activation energy and assume falsified kinetics, you needed to provide proof that for both the data points that you were given, the Thiele modulus is larger than 20. So in some of the tests, for instance, your initial temperature was at, I think, 700 Kelvin, and the temperature was reduced to 500 Kelvin. So in this case, you actually moved from the internal diffusion limited regime to the in-between regime, and you could not make the assumption that you are in the range of values where you have a straight line Lin-K Arrhenius dependence on the apparent activation energy. In some of the other tests, though, you were given a value at temperature 1, 600 Kelvin, and your temperature was increased. So if you calculated the Thiele modulus, and in all cases you had to calculate the Thiele modulus from the eta equation. So you know your eta, your effectiveness factor. There's a first order equation for the Thiele modulus eta relationship, so you could calculate the Thiele modulus for case 1. Since you now know that your temperature is going to increase, particle diameter decrease, you know that I am going to see a further increase in the Thiele modulus by considering the equation. So I don't have to recalculate it. I know that since it's larger than 20 already at my first data point, there will definitely be an increase in Thiele, and I can safely assume that I am in the apparent or falsified kinetics regime. So lastly, if you now took this as the slope for your apparent kinetics, this slope over there between the two data points, just graphically represented here, you can see that the slope of that serrated black line is not the one that you are interested in calculating. So for all these lines, the slope, yes, the slope is indeed the same, and it is the true activation energy divided by 2. But you must realize that this apparent K0 dash does not cancel out because I made a change in the particle diameter. So careful when you calculate that slope. You need to consider the effect of particle diameter in the K0 dash apparent. So the fact that this intercept is changing means that I could not use these 2 points and that just calculate the slope between them to get my apparent activation energy. So if you wanted to prorate correctly, you need to include that effect. And if you consider that whole equation for K0 apparent, you would see that it's inversely proportional to the particle diameter. All the other terms, in fact, if you substitute in there, will cancel out, but you will be left with a dp1 and a dp2. So multiply by dp1 over dp2, and now I can calculate the slope by taking the ln of the numerator and the denominator versus 1 over t1 and 1 over t2.